Hi students, 12th standard chemistry, unit 5 coordination chemistry. So in this session I am going to teach you the example for valence bond theory. Already we have seen what is valence bond theory and its postulates. Okay, in this video I am going to give the example for valence bond theory. Okay, so I have taken one complex which is nothing but hexacyanidoferrate 3 ion. Okay, this is the complex that I have taken to explain the valence bond theory. Okay, the first thing I have to write down the atomic number of the central metal atom. Here, which is the central metal atom? Here Fe is the central metal atom, which is nothing but the ion. Okay, so ion is the central metal atom and the cyanide is the ligand. Okay, and this is called coordination sphere, and the overall it is said to be the coordination entity. Okay, what is the atomic number of iron? The atomic number of iron is 26. Okay, that is the first step. Then the next one, I have to find out the oxidation state of the central metal atom. Okay, what is the complex? Fe CN6 3 minus. This is our complex. Now I am going to find out the oxidation state of the central metal atom. Okay, for this ion I am going to find out the oxidation state. So I am going to keep this as X. How many ligands are there? 6 ligands. So for cyanide ligand, what is the oxidation state? -1. So I am going to keep as it is. Okay, then do the simple calculation. X minus 6 equal to -3. Then X equal to 6 minus 3. What is the thing that I will get? X is equal to +3. Okay, so the oxidation state of the central metal atom iron, which is nothing but +3. So iron is in +3 oxidation state. The first step we have to find out the atomic number, and the second step we have to find out the oxidation state of the central metal atom. Then the third one, I have to write the electronic configuration. You know how to write the electronic configuration. So the atomic number of iron is 26. I am going to write the electronic configuration first. Let me write the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, so if I count the electrons, I will get the total number here. Okay, 2 plus 2 4, 4 plus 6 10, again this will on 10, 10 plus 10 20, 20 plus 6 26. Okay, so this is the electronic configuration for iron. Okay, now I am going to take the outermost shell. This is called outermost shell, 4s2 and 3d6. Okay, so this is the outermost shell. I am going to take this. Okay, so let me draw the outer orbital of a metal first. Okay, before that the oxidation state of a metal ion is +3. Fe is in +3 oxidation state. Okay, if you are like if it is given like this, means how I have to write, I have to remove, if it is 3 plus means I have to remove 3 electrons from this. Okay, let me write like this, 3d6, 4s2. Why I am writing like this means, to remove the electron from the s orbital is very easy when compared to the d orbital. Okay, so it is the simplest orbital. First we have to remove the electron from the s orbital, then we go to the d orbital. Okay, I have to, if it is 3 plus means I have to remove 3 electrons from here. Okay, so if I remove 3 electrons, 2 electrons from s orbital and 1 electron from d orbital, the remaining I will have 3d5. So let me write that 3d5, 4s 0. Okay, so at last I have written 3d5 4s 0. This is our outermost electronic configuration. Then I have to write the outer orbital of a metal. Okay, already we know that which orbital will possess how many degeneracy orbital. If it is s orbital means it will have one degeneracy set. If it is p means it will have 3 degeneracy set. If it is 3 d orbital means it will have 5 degeneracy set. So our electronic configuration is 3d5. So I have to draw the d orbital degeneracy set. 1, 2, 3, 4, 5, then 4s orbital. It is having only one degeneracy set and we are having 4p orbitals. So it is 3d5, 4s0 and this is 4p orbital. This is also empty. Okay, I am going to fill the electrons. Okay, 3d5. How I have to fill the electrons? Already we have studied the filling of orbitals in 11th standard chemistry. Okay, we have to, while we are filling the orbitals, we have to follow the half-half principle. What the rule says, until all the available orbital is filled, then only the pairing is taking place. Okay, at least each degeneracy box will fill first, afterwards only the pairing will take place. Okay, so I am going to fill the electrons by following the half-half principle. So 3d5 means 1 electron, second electron, third electron, fourth electron and this is the fifth electron. I have filled the electrons by following the half-half principle. Okay, then I have to find out the nature of the ligand. Okay, in the spectrochemical series it is given how which is strong field ligand and which is weak field ligand. Okay, by using the spectrochemical series we can say that cyanide is the strong field ligand. Okay, cyanide is the strong field ligand. Now I am going to write the outer orbital of central metal atom. In the presence of a ligand I am going to write. Okay, before writing that you should know what is the role of the strong field ligand. If it is a strong field ligand, it can pair up the electrons. If it is weak field ligand, there will not be pairing take place. Okay, there won't be pairing take place. Okay, so since it is a strong field ligand, the electrons which is present in the d orbital will tend to pair itself. Okay, so let me write here. This is d orbital and this is s and this is p orbital. Okay, this is 3d orbital and 4s orbital and 4p orbital. Okay, I am going to write the electrons. I am going to pair up the electrons. These two electrons will go to the first two degeneracy set. Already we are having 5 electrons. These 2 electrons will come and pair here. Okay, in this way I can get the electrons. This is 3d5. The remaining I am having how many degeneracy sets? Empty 1, 2, 3, 4, 5, 6. Okay, then I have to write the hybridized orbital. How to write the hybridized orbital? Since our compound contains 6 number of ligands, these ligands will donate a pair of electrons to the d orbital as well as 4s orbital, then 4p orbital. Let me write here. This is d orbital and this is 4s orbital and this is 4p orbital. Here hybridization will be taking place. What is hybridization? Mixing of atomic orbitals with the same energy. Okay, here it is filled. Okay, remaining, this is d orbital in the sense, d means I am having 2d degeneracy set is empty. Okay, so d2, this is s orbital and this is s and p3. So these orbitals will participate in hybridization. Okay, these orbitals will participate in hybridization. Okay, we are having 6 ligands in our compound. What is the ligand? Cyanide. Okay, these 6 ligands will donate a pair of electrons towards these 3 orbital. Okay, let me write here. Cyanide will donate a pair of electron to the D1. Cyanide will donate a pair of electron, again will donate a pair of electron. Cyanide will donate a pair of electron and so on so. Okay, so in this way it is donate its electron. So let me write the electrons here. 1, 2. Okay, or otherwise how I can write like this. Only one bond. These hybridized orbital I am going to mix together. This is D2. I am taking these 2 degeneracy set from the d orbital and this is s and this is p. Okay, d2 s p3. Okay, cyanide is donating a pair of electrons to these orbital. Okay, in this way I can get the hybridized orbital. Then the coordination number. Coordination number, which is nothing but the number of ligand which is attached to the central metal atom. The number of ligand which is attached to the central metal atom is called coordination number. In our compound 6 ligands are there, so the number of ligands will be 6. Then the hybridization. Okay, we have seen the hybridization D2sp3. D2sp3. The geometry will be D2sp3 in the sense number of ligands 6 means the geometry of the compound will be octahedral. Okay, this is octahedral complex. Here inner d electrons are participated, so it is called inner d transition element. Okay, then the magnetic property, since this compound is having unpaired electron, magnetic property in the sense we have to see the unpaired electron. Okay, here in this case we are having one unpaired electron. It is having one unpaired electron. So if the compound is having the unpaired electron means that is said to be paramagnetic. If it is having paired electron means that is said to be diamagnetic. So this complex contains one unpaired electron. This compound is said to be paramagnetic. Then I have to find out the magnetic moment. The magnetic moment formula is square root of n into n plus 2. Here n indicates the number of unpaired electron. In our compound we are having one unpaired electron. So let me do the simple calculation. Square root of 1 into 1 plus 2. If I do the calculation, what is the value that I will get? 1.7 Bohr magneton. Okay, so in this way we have to find out the properties for the complex which is given to us. Okay, hope it is clear to everyone. Thank you.